The problem is 6.59 in our textbook, and uh, the question asking us to determine V out at t greater than 0. So I know that that's going to be the step response. But look at the given op-amp. I have capacitor 1 and capacitor 2. There's no way for me to combine C1 and C2 together because they are not in parallel, they are not in serial either. So I know that this is going to be the second order circuits because I have two components that can store energy in my circuits. So to solve this type problem, we need to analyze the circuits at t less than 0 and t greater than 0. At the time frame t greater than 0, we need to consider at t equals 0 the transient state and the steady state, which is t equal infinity. So let's analyze the circuits at t less than 0. So as you can see, I already sketched out the circuits. But one more thing really important I forgot. The given V in A U of t. So when I see that, I know that when t less than 0, then U of t gonna be 0, and my V in gonna be 0 volt. When t greater than 0, U of t gonna be 1, and then my V in gonna become 8, and it's actually 2 volt as given. So now when t less than 0, I have no source, nothing. So we don't have anything to charge the circuit. So of course VC1 gonna be equal VC2. Also gonna be the same thing with V out, gonna be 0 volt. So now let's move to the next time interval. When t greater than 0, I like to analyze the circuits at t at the steady state first because at the transient state it's more complicated. So save that to later. So right now at t equal infinity, I know my V in gonna be 2 volts as given. And now you can see that when the capacitor fully charged, it's gonna behave like open circuits. So I have C1 and C2 as an open circuits right here. Now we're gonna go ahead and write the KCL, the first KCL at VA. So I have VA minus V in, which is 2 volt, over R1, which is 5,000 ohm, plus VA minus VB over 10 kilo ohm, plus IC2. But now look at IC2. It's open circuits of C2, so IC2 actually 0. So just cross the term out. So now our first equation is complete. Now we're going to move into the second KCL at VB. I have VB minus VA over R2 plus IP, I call it IP. And this one right here, we know like one of the two really important property of the op-amp, the current flow in the op-amp right here and right here is actually 0. So I know that my IP is 0, so I just plus 0. And right here, IC2, my IC1, it's also 0 because it's open circuit. So see it right here. So by this, I can make a statement that VA equal VB. Now plug it back into this equation right here. And you guys can see that the term right here, VA equal VB, right? So when VA minus VB, it's going to be 0. So the term right here is going to be 0. So I have the first term, VA minus 2V over 5,000, going to be 0. So therefore, I know VA at infinity equal VB at infinity equal 2 volt. Now we need to find V out because the question asking the main character right here is V out. So we need to determine V out at infinity. So let me highlight this note right here. So the virtual short right here. So there actually is VB right here too. So we can say that right here, the note right here is 2 volt. So I can have the current flow down, the current flow up. This current flow into the op-amp is 0. Let's call this one a IR3, okay? So now I'm going to go ahead and write the equation for the KCL at this note right here, 2 volt. Okay? So 2 volt minus 0, so I'm writing the current flow down this way, over R4, 20 kilo ohms, plus 2 volt minus V out, over 12 kilo ohms, is 0. And now I can solve for V out. At infinity, when you do the algebra a little bit, you solve it out, and you get 3.2 volt. So here's the all of my important value that let's highlight it and save it for later. So now we're going to move on to the next thing. The most complicated one, transient. So you see I put back everything into the given circuits, like the original given circuits. Right here. C2 and C1, just like C2, just like the capacitor. So now I'm gonna write the KCL right here. Let's call it VA and VB again, because we've been calling VA and VB. Write the KCL at VA. I have VA minus V in, which is 2 volt over R1. And my R1 is 5,000 ohms plus VA minus VB over R2 and have R2 is 10,000 ohms and plus IC2. IC2, that current flow through IC2 gonna be C2 B dt. Voltage across the C2. Voltage across the 2 this time is gonna be VA minus V out. This is my first equation in transient state. Then move on to the second equation. Okay. We're gonna write a second KCL at VB. I have VB minus VA over R2, 10,000 ohms, plus the current flow in here is still going to be 0. And the current flow down here, IC1. IC1 going to be C1 dt. Voltage across C1 is actually VB minus 0. Just write VB equals 0. So that's going to be my equation 2. Next, I'm going to try to derive the third equation right here, the KCL right here. So because the main question is asking for V out, so we need to write something that involves V out in here. I'm gonna have, let me highlight so you can see what is this, VB, virtual short, right here. So this is still gonna be VB. So I'm gonna denote it right here, VB. So my KCL gonna be VB minus VR over R3. My R3 is 12,000 ohms plus VB over R4. My R4 is 20 kilo ohms. And the current flow this way is 0 because flow into the op amps, right? So it's 0. That's in my equation 3. So because the main character is V out, so I try to solve for V out. I try to solve for VB in terms of V out. Because I just want my ultimate equation is something with V out, right? My variable is V out. So I need to solve for other variable in terms of my main variable. Just solving this equation can help me solve for VB in terms of V out. So when you do the algebra a little bit, you can find out V out actually 6.625. No, my bad. I'm sorry. I take it back. Oh yeah, actually it's correct. Gonna be 6.625 V out. Let's call this in my equation 3. My equation 3. Now I want to turn everything into just one variable because right now I have VA, VB, and VI as my 3 different variables, right? So I'm just gonna try to substitute back. I'm gonna substitute equation 3 into equation 2. So I have 0.625 minus VA over 10,000 plus C1 dBT for 625 VL. And then when I solve it, I'm going to have this equation right here is VA equal 0.625 VL prime plus 0.625 VL. I do have, I did work it out before, so I have this no equation right here, but I will post my paper writing, and it's I do extra algebra in there so you can see it. Anyone have a question? So now I'm going to sub equation 4 into equation 2 and equation 3 into equation 1. I'm going to have a new equation. Just you substitute VA, you right here, you can substitute VA in here, in here, and in here. And also you guys can, and you substitute VB equal 0.625 VL in here. And let's see what we're going to get. We're going to get something, after I reduce everything, I'm going to get 1.25 times 10 to the negative 4 VL double prime. Should I do that or should I just work out everything because it's going to be a long thing? Or maybe just do it because it's fun anyway. Okay, when I substitute everything in, I'm going to have 0.625 VL prime plus 0.625 VL minus 2, everything over 5,000 plus 0.625 VL prime plus 0.625 VL minus 0.625 VL over 10,000. This right here, cancel out. Plus C2 dt 0.625 VL prime plus 0.625 VL minus VL over equals 0. Now, this guy right here, when you distribute inside, you can have VL double prime. This right here can be VL prime. So I think that I almost guess my signal differential equation, right? After you do everything and reduce it, I'm going to get this guy. 1.25 times 10 to the negative 4 VL double prime. Because that's how I actually did term right here. C2, when I issue it in here, I get this term right here. Plus 1.125 times 10 to the negative 4 VL prime plus 1.25 times 10 to the negative 4 VL equal 4 times 10 to the negative 4. I'm going to reduce the first 1.25 times 10 to the negative 4 for every single term. So I multiply both sides by 1 over 1.25 times 10 to the negative 4. So my second order differential equation is going to look like this. Plus 0.9 VL prime plus VL 3.2. And you guys can easily see that this is A, B, BE1. And this is my C. So now I can determine alpha is A over 2, that's actually 1.45, and P over S. My omega naught gonna be D, it's actually 1 radian per second. And this is gonna let me know how damping our circuits, right? Because alpha is less than omega naught, so I know that's the under damp. Sorry for my handwriting, I know it's hard to write in here. It's not really good at all, I'm sorry. Okay, so because I know it's under damp, so I need to find omega D, which is omega naught square minus alpha square. Gonna be 0.9 radian per second. This is radian, I'm sorry. This is radian per second. Yeah. So now I'm going to determine D1. D1 actually VL at 0 minus VL as infinity. How do we determine V out at 0? So let's go back to this right here. So we know that the voltage across the capacitor cannot change spontaneously. So at t less than 0, the voltage across the C1 right here is 0. And voltage across C2 also 0. So it's going to take this voltage, go to the initial state at the next time interval, which is t greater than or equal 0. So when at the t equals 0, this the voltage is still going to be 0. The voltage is still going to be 0. And we have the voltage right here, right? So everything right here is going to be 0. And that thing up here is 0. So V out also going to be 0. I mean V out at time equals 0 going to be 0. And V out at infinity, we saw it right here, 3.2. So have it going to be negative 3.2 volt. Now we're going to solve the 2. V2, we need to figure out what is V out prime at 0. Now how do we do that? Are we running into an issue? V out going to be equals 0, right? Now take a look at equation 4. This equation right here that I have. So VA right here, I can solve for V out prime. Gonna be 1 over simplify. VA minus VA 0. And V out 0, right? Yeah, so now how do we determine VA at t equals 0? Go back to this circuit again. So we have everything in the green node I highlight is 0. And everything in the green node is 0. But actually, the C2 is also VA. So therefore VA is 0 too, right? So now it's become easier for us because it's 0 right here. This is 0. V out as t equals 0 also 0. So the whole thing right here is 0. So the whole thing right here is 0. So now I have V out prime at t equals 0, which is 0. Yeah. So D2, I have it right here. D2 going to be V out prime t equals 0. So that it's just 0 plus alpha V1. Alpha is 0.45. And then our D1 a minus 3.2 over, I believe, omega naught. Omega D. Okay, omega D is 0.89. It's going to be minus 1.62. Oh. Now we just plug it in our equation and we have it complete. Plug it in right here, the equation right here with V out. A T going to be G1. And our G1 is negative 3.2. Well, cosine omega D is 0.89 T plus D2. D2 is also minus a negative number. Minus 1.62 V psi 0.89 T. Everything times e to the negative alpha, which is negative 0.45 T plus V out at infinity is 3.2 volt. You can do a little bit algebra to bring it to the front and make it look prettier. I like it, put a positive number in the front first. So I factor out negative 1. And then 3.2 cosine 0.89 T plus 1.62 sine 0.89 T. Everything e to the negative 45 T. Yeah, I should go to put over here. Thank you so much for watching. Bye.